Welcome to the Atlas Copco Seminar Series. Today's subject will be press theory. Our agenda, we're going to do a little introduction, cover some basic press terminology, go over the basics of material science, what goes into designing a press joint, and then also several examples of press strategies. First of all, why press things together? So press is a way to manually connect two parts. It's simple, it's reliable, and it's cost efficient. First thing we're going to cover is some press terminology. So some of the basic terms used when we're talking about pressing. The first one that we need to understand is force. Force is an external pressure either focused toward or pulling away from an object, applied by either another object or something such as gravity or magnetism. So the example we have here is a man pushing a box up a ramp. The man actually represents the press. What he's pushing against, the arrow F, represents the opposing force. And in this case, that results from the slope, the weight, and the surface finishes of the ramp. So force is a push or a pull on an object that results from the object's interaction with other objects. So we need to keep that in mind. It's not just the force we're applying. That force is going to vary depending on the interaction with the other objects involved. Force has to be measured. So the basic unit of measurement in force, the metric unit is a Newton, and the English or the non-metric measurement is a pound force. So what is a Newton? It's how much force it takes to move 1 kilogram at 1 meter per second squared. So different units of force. Here we have an example of a conversion site. So depending on what units we're talking in, we can use a conversion table to convert so that we're all speaking with the same measuring units. So 1 kilonewton is how typically presses are sized by kilonewtons. And 1 kilonewton is approximately 225 pounds force. So what does that mean? If you weigh 225 pounds, when you're standing, you're exerting approximately 1 kilonewton of force. The other important term that we're going to use when we're talking about press is stroke, or the unit of measure for the distance that the object is going to move. And again, that can be expressed in millimeters if we're metric, in inches if we're using SAE, and it's the linear movement of the object. There's a couple of different ways that we can measure that stroke, and those are absolute positioning and relative positioning. And here on the screen, we have an example of the two of them. In relative positioning, the press calculates the distance from the latest point. So on the top chart, we can see the press moved from 0 to 49. So it moved 49, in this case, millimeters. And then the press moved from 49 to 54. So it moved 54 millimeters. When we look at that in absolute terms, absolute positioning, the press calculates the distance from a fixed position or a reference point. So the press in the bottom chart moves to 49 millimeters, which means it moved 49 millimeters. It then moved an additional 54 millimeters forward, but it moved to a position of 103 millimeters. Now we'll explain that a little bit more on the next slide. Absolute is where the press moved to. So it moved 54 millimeters, and then it moved 49 millimeters. Relative is how far the press is moved. So it moved 54 millimeters to a position of 54 millimeters, and then it moved to a position of 103 millimeters. The difference here is absolute is very well suited for operator control presses. So if the operator releases the trigger, the press is stopped. We don't really know where in its stroke it stopped. But when we resume the cycle, we know where 0 was, and then we can move to the desired position from there. So here's an example of where that comes into play. If we program the press for 100 millimeters and the operator releases the trigger at 50 millimeters, then he restarts the cycle. In the top, we're using absolute positioning. So he released the triggers at 50 millimeters. The press was commanded to a position of 100 millimeters. So when he resumes the cycle, the press ends up at 100 millimeters. If we're using relative positioning, he released the triggers at 50 millimeters. When we resume the cycle, we've commanded the press to move 100 millimeters. So at the end of that cycle, the press actually winds up at 150. So we can remove a lot of the interaction or the influence that the operator has on the system by using absolute positioning. The next basic term when we're talking about press is going to be speed. And speed is how fast the press moves. Again, that's typically measured in millimeters per second. Of course, we can also do inches per second. That's just one of the settings that we do. Typically, there's going to be at least 2 speeds used in a pressing process. Approach speed, which is your high speed transport time, so where you're moving prior to actually reaching the part. And then press speed, which is going to be your low speed, which is the actual performing of the work on the part. In addition to these 2 speeds, there's also some desired flexibility. So the ability to shift speeds. And we can shift speed based off of force, based off of a stroke, so where the press is, based off of a position, or even off of an external input. And again, we also have to control how quickly we accelerate and decelerate. So we can ramp up or ramp down that speed, again, based off of when we get to a certain force, when we've reached a stroke or position, or again, off an external input. So speed's another term that we're going to use. And again, typically your customers, your applications are going to use at least 2 speeds, approach and press, but it's also desirable to have a lot of extra flexibility in that to be able to shift the speeds and things like that. So here we have a little example so we can help you visualize it. So approach speed is where the press moves very quickly. This is where we have the best opportunity to save cycle time. And then the low speed or the actual press speed. And again, this is where we want a little bit more control. So we're going to be running a little bit slower. So you see the press goes fast. Once we get to a certain point, then the press slows down. So in speed, you're typically going to have these 2, the approach and the press, but it's also desirable to have that additional flexibility to be able to shift speeds and change speeds within your process. Another important factor or another term that we're going to come up to is friction. So friction is the resistance that one surface has when it encounters or tries to move over another surface. Friction is very important because at the end of the day, friction is what we're trying to overcome with the press force, and friction is also what keeps everything together when we're done pressing it. Another term you're going to run into is force rate. So how quickly the force is being applied to the joint. So steeper is harder, so it's harder to press the 2 pieces together. And in the chart we see that at the beginning of the cycle, where we're first starting to engage the part, it's very difficult. We've got to we see higher friction, so the force rate is higher. A shallow slope indicates a softer joint, so it's easier to put together. And then in the next section of this chart, we can see now the part is engaged, it's collapsible, so now the force rate is a little bit shallower. And then at the end, when we finally bottom out, we see the force rate once again climbing because we're seeing the higher resistance. We can take this value and we can check it to make sure that the parts are being put together correctly. So if it's too loose, we can see that by a shallower force rate. If it's too tight, we can see that by a steeper force rate. And these are checks that we can incorporate into the program making sure that we're putting the parts together and that we're putting the parts together correctly. When we first start talking about press joints, one of the things we're going to talk about is fits. So fits is how the two pieces are supposed to go together. We have clearance fit, and a clearance fit just guarantees that there's going to be clearance in the joint. It's always going to be a little bit loose. We then have interference fits. So interference fits guarantees that it's always going to be tight. So there's always going to be some sort of interference between the two parts we're putting together. And then we have transition fits, and transition fits can be both clearance or interference depending on the tolerance. So part tolerance also comes into play here, and that's another thing that we can use the press for, is to make sure that we are within tolerance. An example of a clearance fit, something that most of us do every day, is when we plug into the wall. We need a little bit of interference so that the electricity can flow through that plug, but we don't want it so tight that we can't easily plug it in and unplug it. So the shaft maximum, or the plug maximum, is always going to be a little bit less than the hole minimum. So they're easy to put together, they're easy to take apart. So another example we have over here is a spline. That spline, we want to be able to easily take it apart and put it together. Those are examples of clearance fits. So yes, it's going to take a little bit of force to plug it in, but we're going to be able to plug it in and unplug it very easily. It's a clearance fit. Transition fits. Transition fits are usually used when we're putting two components together that we don't want it to rotate or slide, but we may need to be able to disassemble it easier. For example, a pulley mounted to a shaft. It's snug, but it is still able to take apart. So one of the easy examples is Legos. When we put together two Lego bricks, we first hear them kind of click and they stay together. And they stay together pretty well. But if we really had to, we could take them apart without doing damage to either of the two pieces. So Legos are an example of a transition fit. And then finally is an interference fit. When we put these two parts together, we want them to stay together. So the shaft minimum is always a little bit larger than the hole maximum. So here we have an axle going on to a gear. We don't want that to come apart. So that's going to be an interference fit. Another simple little example is a cork in a bottle. When we put that cork in, we want that cork to stay in. If we're going to take that cork out, it's going to take a little bit of force or more force. It's going to come apart, but it's not going to come apart too easily. So in interference fits, the parts are intended to stay together. So that was some of the basic terminology that we're going to run into when we're talking about press. And now we're going to get into a little bit of the material science involved with press. So the first one we want to talk about a little bit is thermal expansion. And thermal expansion is the property of a metal or material that it'll expand on a hot day and it'll shrink on a cold day. Different metals have different thermal expansion rates. For instance, cast steel changes quite a bit, well, relatively speaking, when compared to titanium just by temperature changes. Different materials will expand at different rates. So if we're putting together two different pieces that are made out of two different materials, they're going to expand at different rates. It's going to have a larger effect on them. If we're doing it with two similar materials, it's not going to have a larger effect. But the main reason is when we heat something up, we're making the atoms or the molecules move, and that causes them to expand a little bit. Good example is water in an ice cube tray. When you fill up your ice cube tray part way, but when it freezes, it gets a little bit bigger, so it expands. That's thermal expansion. And we can use that when we're pressing as well. So we have two examples here. One, we're pressing a shaft into a gear. To make it easier, we're going to supercool that shaft. The shaft's going to shrink, and it's going to be able to go into the gear easier. Another example is warming makes things get bigger. So here we're putting a bearing onto a shaft. We're going to heat up that bearing. That's going to make it expand a little bit, and it's going to make it easier to put that bearing onto that shaft. So thermal expansion is something we have to keep in mind when we're talking about press. Another one is the module of elasticity. So the module of elasticity is the ability for a material to resist change. So softer materials are easier to change, so they'll mash out of the way a little bit. Harder materials will not. So again, plastic is a very soft material. When we put it together, the material is going to be able to move, and it's going to be easier to put the two pieces together. Where if we go to the other end of the scale with diamonds, diamonds are very hard. They're not going to change. They're not going to be able to deform very easily, so it's going to be harder to put together. So basically, the stiffer a material is, the more force is going to be required to put those materials together. Surface finish. So surface finish goes back to what we talked about earlier, friction. A rougher surface is going to be difficult to put together. A smoother surface is going to be harder to put together. And that's all because of the interference, or the how much of the material we're going to have to rub across or displace in order to put the two pieces together. So we need to keep in consideration material finish or surface finish of the materials as well. So we took two pieces of glass, they're going to slide together across each other very easily because there's not going to be much roughness. If we took two pieces of sandpaper and tried to slide them together, that's going to take more force because there's going to be more roughness or more interference between the two pieces. So the effect of friction, so again, surface finish gives us the effect of friction. So in the first example, we're using sand casting, so something very similar, something very typical that gets used when we're pressing pieces together. Sand castings are going to have a rather rough surface finish. So when we press two parts with the same fit together in a sand casting, it's going to take a higher force for those two pieces to go together. Or if you took the same clearances and did it on a super finish or a polished bore or something, now it's going to take a lot less force to put them together. So the surface finish is another important factor when we're talking about press. All right. Next, we're going to get into the design of the joint. So most of the time, our customers are going to go through all kinds of, see what type of fit they need, see what kind of objectives, what kind of surfaces they have, and they're going to design their joints around that. So we've already talked about the first thing. The first thing the customer is going to decide is what type of fit do they need. If they need a clearance fit, so it's going to be nice, easy to put together. A transition fit where, yeah, it's going to hold, but it can come apart. Or are they going to do an interference fit? So this is going to depend on what is the intention of that assembly going to do. Is it going to be something I want to just easily click together or put apart? Or is it going to be something that once I put it together, I want it to stay together forever? And here's just a quick little chart here showing the shaft and then the interference of the shaft with the holes. So in the beginning, bigger holes obviously lead to clearance fit. Medium or mid-size holes are going to lead to a transition fit. And then we have very small holes compared to the shaft size. We're going to get into that interference fit. And again, each of those are going to take a little bit more force. And just as a rule of thumb, clearance is going to take the least, interference is going to take the most. Okay, so in the design of the press joint, the customer is going to make this decision. Here, in our first example, we have an interference fit. And an interference fit, there's always going to be, we see that the shaft is 50, the hole is always smaller than 50, so there's always going to be interference. It's going to be harder to put together, harder to take apart. Next one we have is the transition fit, where we can see the example, the hole is a little bit smaller, or the hole is the same size of the shaft. So it's going to be a little easier to put together, and it is going to be possible to take it apart. And then in our last example, again, my shaft is 50, my hole is always a little bit more than 50, or 50 itself. So that's going to be relatively easy to put together and relatively easy to take apart. So if I were designing, what size hole would I need to use for a 0.25 inch hole? What size should the dowel be for a 0.25-inch hole? The answer is, for a clearance fit, the dowel should always be just a little bit smaller than the hole itself. For a transition fit, the dowel should be the same size as the hole or a little bit smaller. And for an interference fit, the dowel should always be bigger than the size of the hole itself. So again, these are decisions that are made while you're designing your press fit joint, is how do you want them to fit together. Now we're going to get into press strategies. There are two basic strategies to press. The first one is pressing to a stop. So we're going to take this bearing, we're going to put it into the journal, and as we're doing that, we're going to be monitoring it and observing what happens. So transport through the air, nice and simple. Interference as we're going through the hole, and then when we get to the bottom, we see that peak in force. So the part has bottomed out. So this is pressing to a force. And when we're pressing to a force, our primary quality check is going to be depth or stroke. How far did we move? We can also do a more complex force profile. So here we got an example of a part going in, and there's 3 sets of O-rings. We're still going to press to a force. We're going to bottom out that part, but as we do it, we're going to be doing some monitoring. So as we get to that first bit of interference, whether that be an O-ring or something, we see a force rise. As we go further down, we get to the second O-ring, we see an increased force because now there's more friction between these two parts. And when we get to the third one, we see another force rise. And again, during the pressing process, we can check each of these levels to make sure that those parts were where they were supposed to be. And then finally, when we get to the bottom, then we see the main force rise. We've now pressed to the stop, so we there see the force. And again, this is a complex force profile, but again, at each of those points, we can check and we can make sure that this assembly is being put together correctly. So when we press to a force or press to a stop, depth or stroke is our quality check. So if we get there, but we didn't move far enough, perhaps our hole is too shallow. That would result in a low stroke. Too deep, a high stroke. We're going to set these limits based off of actual production. So one of the important things is we need to be able to run parts. We need to see what the normal distribution is, and then we can set our limits. We are able to detect upstream issues. So we can see if the holes are getting shallower or if the holes are getting deeper. Maybe something needs to be adjusted further upstream in the production process to ensure the quality of these parts. The next basic press strategy is pressing to a depth, where we may or we may not see a change in the force profile. But force is now our quality check. So we can use force to make sure that the hole is good or the hole is correct. If the hole is too small, we're going to see higher forces to get to the same position. If the hole is too large, we're going to see lower forces to get to the same position. So again, in the press operation here, we can detect upstream issues. Maybe the drill bit is wearing out, so the holes are getting smaller. Maybe the drill bit is loose and it's wobbling, so the holes are getting bigger. So we can do quality checks in the pressing operation to make sure that things before that process were done correctly. One of the other things that we do quite a bit when we're pressing a part to a certain depth is instead of letting the press stroke control that process, we're going to allow the tool to control that process. So we're going to manufacture our tooling such that it always puts the part in the same place or the right depth based off of when it bottoms out on the shoulder of the tooling. So we're putting the part to a depth we're actually controlling with force. The reason we do this is it's much easier to verify. If I'm letting the tool control the depth, all I have to do is check the tool. If it's actually the parts, then I have to check every single part that I do. Force is actually the control. So now I'm looking at high stroke or low stroke to make sure I did the right thing. And I'm using force to monitor, to verify the hole size and to verify the shaft size. So again, we're going to set these limits based off of actual production numbers. But we're going to still be able to do quality checks so we can eliminate checking stations. And then the final thing to consider is the right tool for the right job. If I'm pressing very, very small parts together, I don't want to use a monster press. If I'm pressing big parts together, I'm not going to get there with the small press. So it's very important to make sure that we size the press correctly for the parts that we are assembling. So thank you for listening to and viewing our Atlas Copco seminar series on press theory. If there's any further questions or any comments that you'd like to make, please feel free to contact Atlas Copco at the email address that you see on your screen.